How much time are you spending just moving data around just to get it into one place so you can finally search it, query it, or analyze it? That's wasted time. And today, we're going to fix that. Welcome to From Silos to Insights, a mini-series of videos that will show you how to unify your data investigation and eliminate the friction of needing to move data around in traditional data management. Before we jump into the workflow, it's helpful to step back and look at the bigger picture. Federated Search is not just a single feature or another connector. It supports a wide range of use cases, from threat hunting and investigations to compliance and historical analysis across data sources like Splunk S3, Security Lake, Machine Data Lake, Azure Data Lakes, Snowflake, DDSS, and more. The bigger idea is simple. Federation gives customers a consistent way to work with the right data in the right place for the right job without constantly moving it around. No matter where your data lives, it's important not to think of this as an either-or decision. Instead, think of it in terms of which approach tends to play the primary role for a given customer or use case. On the left are environments where Machine Data Lake is often the center of gravity, usually because customers want a turnkey, Splunk-managed approach, less custom lake engineering, and a strong AI-ready machine data foundation. On the right are environments where Federated Search tends to play as a larger strategic role, for example, when data needs to stay in place because of residency requirements, shared lake usage, distributed ownership, or the cost of moving large volumes of data. And for the most critical real-time monitoring use cases, the Splunk Index remains the highest performance tier. These decisions can be made at the strategy level or tuned for specific data sources and the source type. Federated Search is positioned as the connective layer across a distributed data ecosystem, helping customers work across data lakes, schemas, teams, and tools without treating Federation as just a point search feature. The key idea is that Federation should support real workloads like investigation, threat hunting, compliance, and historical analysis, and to be used where it makes sense from a cost and performance perspective. Now that we've covered the big picture, let's shift into the specific focus of this video. Apache Iceberg REST with AWS S3 matters because it gives Splunk a practical way to search security data where it already lives. The data can stay in S3, organized as Iceberg tables, while Splunk presents it as a governed federated dataset for analysts. That pattern is useful when teams have historical firewall, proxy, cloud, or application telemetry in object storage and do not want to reingest all of it. Splunk Cloud can still drive the investigation experience, while AWS keeps the data lake storage model. The important thing is the handoff. FS Nessie owns the AWS side, including the REST endpoint, the catalog, Nessie metadata, and the S3 table files. Splunk Scraper owns the Splunk side, including the data management connection, the dataset, and the SPL2 search validation. That is why this topic belongs in the Federated Search series. It connects a real operational question to a repeatable pattern. Keep historical data economical in the lake, expose the table through an open catalog interface, and give analysts one Splunk search surface for validation and investigation. Before we walk through setup, anchor the architecture. Splunk Cloud is the search surface. The analyst writes SPL2 against a federated dataset, and Federated Analytics needs a catalog endpoint that can explain where the Iceberg table lives. The AWS side provides that endpoint through CloudFront, an application load balancer, and an EC2 host running Nginx and Nessie. The public path is intentionally simple for Splunk. CloudFront gives a stable HTTPS name. The application load balancer routes that traffic to the Nessie host. Nginx separates the external paths like /iceberg and /API v2 from the local services. Nessie resolves the branch namespace and table metadata, and Iceberg REST exposes the table operation. The data path is different from a copy path. S3 remains the warehouse for metadata, manifests, and Parquet files. AM and bucket permissions control who can read the objects. Splunk uses the catalog to understand the table, then reads only what the search needs. With that shape in mind, the setup section focuses on the service boundary that makes this reachable and searchable. For the AWS portion, do not think about this as a template walkthrough. Think about it as a small Apache Iceberg REST service boundary. The important pieces are the EC2 instance, Nginx, Nessie, Iceberg REST, the application load balancer, CloudFront S3, and the permissions that let the service and Splunk read the warehouse. This is the architecture we are validating. The EC2 instance is the center of the AWS side. It gives us a controlled host for the catalog service and the reverse proxy. In this environment, it runs in the demo VPC, has a private address for service traffic, and a public address for administration and validation. The reason to isolate this on a host is that the REST catalog behavior, local configuration, and service logs can be checked directly. The network layer decides what can reach the service. The security group and subnets define the boundary around the Nessie host and the load balancer. At a high level, Splunk should not need to know the private host layout. It should call the public catalog endpoint, while the application load balancer and security group control the path into the service. The application load balancer is the routing layer in front of the EC2 host. It gives the architecture a service endpoint and health checks instead of tying Splunk directly to an instance. That matters because Iceberg REST calls need to be consistently routed to the working Nessie service, and the load balancer gives us CloudFront is the stable HTTPS edge that Splunk uses as the catalog URI. Splunk does not need to understand the internal application load balancer name or the local port where Nessie listens. It needs the public Iceberg REST endpoint, the Nessie API path for validation, and the OAuth token. S3 is the warehouse, not a staging area. The Iceberg table has metadata files, manifests, and Parquet data under the warehouse prefix. For the enriched firewall dataset, the table data is organized under an Iceberg managed folder and partitioned by event date. That physical layout is what makes the lake searchable without copying every row into a normal Splunk index. The terminal checks prove the service from inside the EC2 host. Nginx is active, Nessie answers locally on the API path, and the Iceberg REST config points to the S3 warehouse and the main branch. That is the final AWS handoff. The REST endpoint is reachable, the catalog knows the warehouse, and Splunk can now use the unchanged data management steps to create the connection and dataset. Now we move into Splunk Cloud data management. The connection starts with the general information page. This gives the connection a name, selects Amazon S3 as the data store, and sets up the object that later datasets will use. The ability selection matters because this connection is for federated search. We are not building an ingest pipeline here. The goal is to let Splunk run searches over S3-backed Iceberg data without moving every historical event into an index first. Storage authentication connects Splunk to the AWS account and role. This is where the trust policy and S3 permissions become important. The role must allow the Splunk tenant to assume it and must allow reads against the target bucket and object prefix. Catalog authentication is the Iceberg REST part. The catalog URI points to the HTTPS endpoint, and the OAuth fields describe the expected token flow. In practice, the build also validates what Splunk actually sends during FAS execution. The review screen is the checkpoint before creation. For repeatable work, this is a good place to compare the wizard values against the FS Nessie outputs and the Splunk scraper defaults before committing the connection. Once the connection is created, it becomes the reusable Splunk object for this data source. From here, the dataset workflow can reference the connection instead of re-entering all of the AWS and catalog values each time. The dataset begins with a Splunk safe name. The user-friendly name was Iceberg Data, but the working dataset name uses an underscore Iceberg Data. That matters because Splunk dataset names can reject spaces in this flow. The dataset configuration binds the Splunk dataset to the Iceberg table. The catalog is main, the namespace is demo, and the table is firewall logs. Those three values tell Splunk exactly which Iceberg table the search should address. The update policy step is where the generated permissions need careful review. The AWS policy must separate bucket-level permissions from object-level permissions, or AWS can reject it as malformed. This is one of the places where a quick copy and paste can break the build. At the end of setup, the dataset is available in Splunk. The setup is only complete when the AWS stack is reachable, the connection exists, the dataset exists, and a search can validate the path. Now that the connector and dataset are in place, we can run the SPL2 investigation. The use case starts with the SPL2 core scenarios. The main point is that a team can use S3 with Apache Iceberg REST API to search S3-backed data as a unified dataset, instead of treating the data lake as separate from the security workflow. For security investigations, that means firewall, proxy, cloud, or other telemetry can stay in S3 and still be searched from Splunk. The analyst experience stays familiar, but the storage model is better suited for large historical datasets. The basic SPL2 validation query is intentionally simple, from the federated dataset Iceberg data. A simple query is the right first proof because it confirms the catalog path, the dataset definition, and the ability to return records before adding investigative logic. The results show firewall log rows coming back through the Splunk search page. This is the key evidence for the video. Splunk is accessing the S3-backed Iceberg table through the configured federated dataset, not through a traditional ingested index. Once the rows are visible, the next move is to look at the fields that matter to the investigation. For firewall data, that usually means source and destination addresses, ports, actions, application context, time, and any fields that help separate expected traffic from suspicious traffic. From here, the analyst can ask practical questions. Which destinations were denied most often? Which source addresses talk to unusual ports? Which regions or applications generated the largest volume? The important part is that these questions are now asked from Splunk, even though the historical data remains in S3. After the basic query works, the same pattern can support monitoring and detection. Scheduled SPL2 searches, dashboards, and summary workflows can be layered on top, as long as the team understands which data lives in S3 and which data should still be indexed directly. A scheduled search does not have to pull back everything every time. The value of the Iceberg table is that the data can be structured and filtered before the expensive part of the work happens. Splunk gives the operational workflow, while table design and partitioning influence how much data the search needs to touch. Partitioning is the performance lever. When S3 data is organized by time, source type, region, application, or another useful boundary, searches can scan less data. The Iceberg table design becomes part of the Splunk search experience. For example, if firewall logs are partitioned by event date and source type, a time-bounded security search can avoid scanning unrelated days or unrelated telemetry. That does not remove the need for good SPL2, but it gives the search engine a better physical layout to work with. The pattern also shows what not to do. Do not treat the lake as a dumping ground with no table design. Do not assume every dataset belongs in federated search. Hot operational data may still belong in a normal index, while colder, larger, or less frequently searched telemetry can fit this Iceberg path. In a real investigation, the simple validation search becomes the starting point. The analyst can add time bounds, filter for denied actions, narrow on a source address, or summarize by destination and port. The key is that SPL2 still becomes the investigation language even when the storage layer is S3. For operations, the pattern can become a repeatable workflow. Start with an exploratory search, turn the useful logic into a scheduled search or dashboard panel, and then decide whether the resulting summary should be accelerated, indexed, or left as federated access depending on cost and response time needs. The design checkpoint is simple. Know what the analyst needs to ask, know how the S3 table is partitioned, and know which fields are reliable. Federated search works best when the table design, catalog path, and SPL2 use case are planned together instead of treated as separate tasks. The final takeaway is that this is a repeatable pattern. AWS provides the data lake, Iceberg REST, and Nessie provide the table metadata path, and Splunk Cloud provides the search experience. Now that we have results from S3-backed Iceberg data, we can wrap up the series flow. As we wrap up, the value of federated search is about giving organizations more flexibility in how they work with data. Not every dataset needs to be fully ingested before it becomes useful. Some data may live in Amazon S3, cloud data lakes, partner environments, archival storage, or other external repositories. With federated search, Splunk lets teams search that data where it already lives, using the familiar search experience analysts already know. That means security, IT, and operations teams can investigate faster, expand visibility, and reduce the friction of moving data just to ask a question. Instead of waiting for onboarding, indexing, or duplication, teams can query external datasets directly and bring the results into the investigation when needed. This creates a smarter operating model. High-value, frequently used data can still be indexed locally for performance and real-time alerting, while historical, compliance, or enrichment data can remain external and searchable through federation. Federated search helps organizations shift from a data movement strategy to a data access strategy. The real value is simple. Keep data where it makes sense, search it when it matters, and bring insights back into Splunk where teams can act. My name is Mark Snyder, and thank you for watching.